A helical gear is a type of cylindrical gear with teeth that are cut at an angle to the gear's axis, rather than parallel to it. This design allows for smoother, quieter operation and higher load capacity than straight-cut gears. Helical gears are commonly used in power transmission systems, such as in automobiles and industrial machinery. They can also be used in pairs, known as a helical gear pair, to change the direction of rotation or to increase or decrease the speed or torque of the system. The formula for determining the pitch diameter of a helical gear is D equals N plus 2, pitch, where D equals pitch diameter, in, N equals number of teeth on the gear, pitch equals helix angle, in, tooth. It is important to note that the formula assumes that the gear is operating at its normal, unloaded position. If the gear is loaded, the pitch diameter will change slightly. Additionally, you can use the formula for torque in the helical gear. T equals F asterisk R, cos, alpha, where T equals torque, nanometer, F equals tangential force, N, R equals radius, M, alpha equals helix angle, rad. Helical gear calculation involves determining the proper parameters for designing and manufacturing a helical gear system. The following are some of the key factors that are considered in helical gear calculation. Gear ratio. This is the ratio of the number of teeth on the driving gear to the number of teeth on the driven gear. It determines the speed and torque relationship between the two gears. 1. Center distance. This is the distance between the center of the two gears. It should be designed such that the gears do not collide or bind during operation. 2. Pitch. This is the distance between the corresponding points on adjacent teeth. It is used to calculate the gear ratio and tooth size. 3. Tooth profile. This is the shape of the gear teeth. It should be designed to minimize stress on the teeth and provide smooth operation. 4. Tooth strength. The material properties and manufacturing process are considered when designing tooth strength to ensure the gears can withstand the loads and stresses of the application. 5. Tooth contact. The gear contact pattern is an important factor in gear system design. The contact pattern is defined by the overlap of the gear teeth as they mesh. 6. Circular pitch. This is the distance between the corresponding points on adjacent teeth measured along the arc of the pitch circle. It is calculated by dividing the circumference of the pitch circle by the number of teeth. 7. Helix angle. This is the angle at which the teeth of the helical gear are cut. It is calculated by dividing the axial pitch, the distance from one tooth to the next tooth along the gear axis, by the circular pitch. 8. Tooth load. This is the amount of force acting on a gear tooth. It is calculated by multiplying the input torque by the gear ratio. 9. Tooth thickness. The thickness of the gear tooth measured at the pitch line. It is calculated by multiplying the circular pitch by the sine of the helix angle. 10. Tooth depth. The depth of the gear tooth measured at the pitch line. It is calculated by multiplying the circular pitch by the cosine of the helix angle. 11. Root diameter. The diameter at the base of the gear tooth. It is calculated by subtracting the tooth thickness from the pitch diameter. 12. Outside diameter. The diameter of the gear measured at the top of the gear tooth. It is calculated by adding the tooth depth to the pitch diameter. 13. Lead. The distance a helical gear advances in one revolution. It is calculated by multiplying the number of starts, the number of parallel threads on the gear, by the pitch. 14. Addendum. The height of the gear tooth above the pitch diameter. It is calculated by adding the circular pitch to the tooth thickness. 15. Dedendum. The depth of the gear tooth below the pitch diameter. It is calculated by adding the circular pitch to the tooth depth. 16. Backlash. The amount of play between meshing gears. It is the difference between the sum of the dedendum of the pinion and the addendum of the gear. Helical gears are widely used in a variety of mechanical applications because of their ability to transmit power efficiently and smoothly. Some common uses include power transmission. Helical gears are often used in industrial machinery and equipment to transmit power from one shaft to another. Speed reduction. Helical gears are commonly used in gearboxes and speed reducers to slow down the rotation of a shaft. High-speed applications. Because of their smooth operation, helical gears are well suited for high-speed applications where vibration and noise need to be kept to a minimum. Heavy-duty applications. Helical gears are strong and durable, making them suitable for use in heavy-duty applications such as mining, construction, and agriculture. Precision positioning. Helical gears are commonly used in precision equipment such as machine tools, robots, and automated systems. Marine propulsion. Helical gears can be used in marine propulsion systems, such as ships and boats, to transmit power from the engines to the propellers. Automotive. Helical gears are used in the drivetrain of vehicles, such as automobiles and trucks, to transmit power from the engine to the wheels. These are some of the common uses of helical gears, and the list is not exhaustive. In any case, the suitability of a gear for a specific application depends on various factors such as torque, speed, load, environmental conditions and so on.